ये लो। और आपको बोल
Sir, we'll just wait for 2-3 minutes, then we'll start so that the students can join in between.
Okay, no problem.
Nisha ma'am, I think we can start the session. It's 2:04.
Okay, Manu. Okay. On behalf of Department of Mathematics, I welcome Dr. Sushil Kumar for this two-day workshop. Dr. Sushil Kumar is an associate professor at Department of Applied Science, Bharati Vidyapit College of Engineering, Guru Gobind Singh Indraprasth University, Delhi. He holds teaching and research experience of over 17 years. Dr. Sushil Kumar has published more than 25 papers in various journals of international repute. His research area is complex analysis. He has delivered numerous invited lectures in various conferences and workshops. He is a reviewer of various international journals. Dr. Sushil Kumar is a life member of Indian Mathematical Society and Ramanujan Society. Dr. Sushil Kumar, sir, welcome to our department.
Thank you, Nisha. Good afternoon, all professors and dear students. First, I thank Professor Neetu Gupta, Chairperson, Department of Mathematics, and Dr. Manu, who provides this platform to me for sharing some facts about complex integration and zeros of analytic functions. In the morning sessions, Dr. Anubhada Gupta has given overview on complex analysis, analytic functions, and the Cauchy-Riemann equations. Further, Professor Akshi Mittal has discussed the Taylor series and Lorentz series expansion as well as singularities. In this sequel, I am sharing some facts or definitions of some theorem and with examples related to complex integration and zeros of analytic functions. So, let me share my screen. Are you all able to see my screen?
Yes, sir, it is visible.
Okay, thank you. So first I start with complex integration. One minute. Yeah. So first I discuss complex integration. For complex integration, we have to discuss some fundamental definitions and concepts which will be used repeatedly in this talk. Let me introduce first curve. A curve or path. Gamma is the complex in the complex plane is the range of continuous function from this interval AB to this complex plane that is given like this. Zt is equal to xt plus iota yt. Here t belongs to this closed interval A, B. Here xt and yt are continuous real valued functions defined on this closed interval AB. And the curve gamma begins with initial point ZA and goes all the way to its terminal point ZB. And the parametric form of this curve is given like this: xt, yt. The curve gamma is the set of all points that is known as the track of gamma or trace of gamma. Somewhere trace word is used, somewhere track is used. A track of gamma, and it is denoted by this symbol. And geometrically, this ZA is a initial point and ZB is is the terminal point, and this is a curve gamma. Next, we come to simple. These are basic definitions which will be used in the concept of complex integration as well as zeros of analytic functions. So simple curve. The curve gamma is said to be simple if it is 1 1. If it is 1 1, it means if for all different values of t, means t1 and t2 are not equal, then zt1 will not be equal to zt2, or in other words, gamma does not cross itself or intersect itself. Like you can see the geometrically, this is example of simple curve, and this is not simple curve because this curve intersect this itself, intersect at this point. So this is not simple, this is simple, and this is also a simple, this is also a simple. So any curve which does not intersect itself, it is called simple curve. You can see another example, the line segment gamma 1, which is given by this expression, is simple curve. Zt is equal to z1 plus t, z2 minus z1. Here t belongs to closed interval 0 to 1, and this is simple curve, and here z1 and z2 are two complex numbers. Another example, another definition, closed curve. The curve gamma is said to be closed if ZA is equal to ZB. It means initial point coincide with terminal point. The curve gamma is called a simple and closed curve, and it is also known as Jordan curve if it is closed as well as satisfy this condition. It means gamma does not cross itself except the endpoints. Means this is simple and closed curve, means Jordan curve. So this is a definition of Jordan curve. This is a definition of closed curve, and this is an example of closed curve. It is also simple curve also. The unit circle gamma 2 given by this expression zt is equal to cos t plus iota sin t. Here t is going from 0 to 2 pi. It is a simple closed curve. It is a simple closed curve. You can see here a initial point here, and terminal point 0 to 2 pi. T is going from 0 to 2 pi. So z0 is equal to z 2 pi. So this is simple as well as closed. Next is smooth curve. So a curve gamma given by the range, given by this range of z from this closed interval AB to C is called smooth if it is differentiable, and continuous on this interval A comma B, and this is non-zero. So this example is not a smooth curve, but smooth curve gamma 1. This gamma 1 is a smooth curve. This is gamma 2. This is gamma 1 is a smooth curve, and but this example is simple but not a smooth curve. Means continuously differentiable curve is called smooth. Smooth means continuously differentiable. So next we come to rectifiable curve. A curve gamma is a rectifiable curve if gamma is a function of bounded of variation, or in other words, gamma is rectifiable is to say gamma has finite length, and length is denoted by this one. So these are some basic definitions related to curves. Next we come to definition contour. Any contour gamma is a sequence of smooth curve. Smooth curve means continuously differentiable. So contour gamma is a sequence of smooth curve gamma 1, gamma 2 up to gamma n, so that the terminal point of gamma k, terminal point of gamma k coincides with the initial point of next smooth curve gamma k plus 1. You can see here the terminal point of gamma 1. Suppose gamma 1 is from this point to this point. So the terminal point of gamma 1 will be initial point of gamma 2. So this is the definition of contour. And this is gamma 1, gamma 2, and another, this is gamma 3. Okay, this is gamma 3, and this is gamma 4, and so on up to gamma n, or this can be written here gamma n minus 1. So this is the smooth curve, definition of smooth curve. Sorry, contour. Next, simple closed positively oriented anti-clockwise contour. This is simple plus closed plus positively oriented means anti-clockwise contour. This is simple. You can see this curve does not intersect itself, and it is closed because suppose this is the initial point and this is also a terminal point. So closed. And positive oriented means anti-clockwise. This is a contour, positively oriented. So we will talk about this contour in Cauchy theorem, or Cauchy integral formula, or complex integration. Okay. So next is a line integral. Before line integral, I want to say complex integration. We can divide complex integration into two parts. Number one, line integral. Number two, contour integration. So first, we have to we have to understand line integration. What is line integration? If gamma is a rectifiable path of curve and f is a function defined and continuous on the trace of gamma. I have discussed trace or track of gamma. Then the line integral of f along this curve gamma is given like this: integration a to b function of gamma t dot d gamma t. The line integral is also denoted like this. This is a basic definition of line integral. So we can see some observation. You can see some observation. Real integration. Integration of fx with respect to x under the limit a to b depends upon the values of limits a and b. Like this, you can see this fact by this simple, very simple example. But in complex integration, it is not true. The complex integration is evaluated either along or around a curve. Means the complex integration of function, complex valued function fz with respect to z from limit z1 to z2 depends upon the path. Initially, I am talking this thing depends upon the path from z1 to z. Of z1 to z2, suppose this is any complex plane. Suppose z1 is here and z2 is here, and there are so many paths: one straight line path, one circular path, one parabolic path, one can be elliptic path, and there are so many paths can be arise from between z1 and z2. So complex integration depends upon the path from z1 to z2. You can see here, if we take this example, we have to integrate this function. fz is equal to z bar, conjugate of complex number z. Z bar is conjugate of this complex number z, and we have to integrate this one from z1 to z2. Z1 is this one, this point, and z2 is represented here in this complex plane. So there may be so many infinite paths from Z1 to Z2. Now in this question, we are taking following three paths. If we take three paths along a straight line, y is equal to 2x. If we take 2x, y is equal to 2x. We take path number 1. This is path number 1. And we can take another path, y square is equal to 4x, parabolic path. Another parabolic path, x square is equal to 1 by 2 y. We can take here. These three conditions, these three curves satisfy these 2 points. So along path number 1, you can see here, along path number 1, from origin to 1, 2, from Z1 to Z2. We have to determine the value of this complex integration. So how can we determine? Put y is equal to 2x or x is equal to y upon 2 in fz. What is fz? Fz is equal to z bar. You can see fz is equal to z bar is equal to x minus iota y. So we can put here y is equal to 2x. So when we put here x is equal to x minus iota y, y is equal to 2x, and dz is equal to x plus z is equal to x plus iota y. So dz is equal to dx plus iota dy. Simple calculation gives us this value 5 by 2. This is value of this complex integration z1 to z2 along path number 1, which is a straight line. Okay, now we come to path number 2. Along path number 2, this is parabolic path, y square is equal to 4x. So according to this parabolic path, we just put the value of x or dx in this, or we can also put the value of y or dy here also. So we put the value of x and dx here, and finally what we get this value. This is along parabolic path, y square is equal to what is 4x, y is equal to 4x. Along this path, this is simple calculation. I am not explaining each and everything. Just I want to show here. Along path number 1, value is 5 by 2. Along path number 2, value is 5 by 2 minus 2 by 3 iota. This is the totally different. Let us see along path number 3. X square is equal to half of y. Half of y, same thing, replace y is equal to 2x square, and similar calculation as done here. And finally we get 19y6. So what we are seeing here, we are observing here along three different paths, the value of this line integral is different. So one is 5 by 2, another is 5 by 2 minus 2 by 3 iota, and third one is 19y6. So the value of this complex integration depends on the path of integration. So in the real integration, finally what we observe, in real integration, value of integration depends on the end point. It means limit point, but in complex integration, value of integration depends on the path of integration from Z1 to Z2. But there are many some other reasons, but there is some remark. And if function fz is analytic, then the value of this integral does not depend on the path. Will depend on the endpoints. If fz is analytic function, if this fz is analytic function, उसमें क्या था? In the previous example, we had fz is equal to z bar. This is not analytic function. This is not analytic function. But if we take instead of this z bar, like e to the power z or sin z or cos z, z square, any analytic function if we take, then the value of complex integration does not depend on the path from z1 to z2. It will be depend on the endpoints. So this complex integration is independent of path. You can verify by this example. I am taking here z. Fz is equal to z. Earlier it was z bar. So if we take uh, fz is equal to z here, this is analytic function. And if we take three paths along straight line y is equal to x, along another parabolic path y square x, and another parabolic path x square is equal to y. If we take these three paths, so according to this statement, value of this complex integration along path 1, along path 2, along path 3 should be equal. So let us see along path number 1 y equal to x, we get the value of this complex integration is iota. Along path number 2, y square is equal to, which is parabolic path, y square is equal to x. Y square is equal to x. So this simple calculation gives the value of this complex integration is iota. And along another parabolic path, x square is equal to y. What we get? We get another iota. So therefore, the values of complex integration along path number 1, straight line path, parabolic path, y square is equal to something, another parabolic path are same. Okay, the values are same. So the value of complex integration means line integration does not depend on the path. Okay, so this is the one fact. And we come to complex integration of function. This is around a contour C. Here, mostly in questions or theorems, this is simple closed contour. Here, so this is called contour integration, and this is always anti-clockwise. Here we take anti-clockwise direction. So you can see one example. This is not analytic function. C is the straight line. Another example of previous one what I have discussed here. So no need to explain this one. So I am skipping. Next, we move to contour integration. So for contour integration, for understanding of contour integration, we have to discuss first simply connected domain. What is simply connected domain? Any domain D is set to simply connected domain if all interior points of the curve C lie in the domain G. Lie in domain D means where C is the arbitrarily simple closed curve in domain D. Means you can see here, this is simply connected domain. In other words, if we take this structure, and if we shrunk this structure from towards the origin, then if we get one point, then this is simply connected. And if we have a hole, you can see simple triangle, this is simply connected domain by this definition. But if we put here a hole, then it will not be a simply connected, because this does not satisfy this definition of simply connected domain. So with hole, this is not simply connected. This is one hole here. Interior, all the points of curve do not lie in this domain. So D is not simply connected domain due to this one hole. And if it is not simply connected, Then this is a multi-connected domain. A domain which is not a simply connected, it is called multi-connected domain. Okay. A domain with one hole, you can see here, it is one hole. This is called doubly connected domain. If any domain has two holes, then it is triply connected, and so on. More than two holes, it is called multi-connected domain. Okay. And we can convert this doubly connected domain or triply connected domain or multi-connected domain into simply connected domain by inserting a cut. By inserting a cut, you can see here, this is doubly connected domain. If we insert one cut here, if we insert here one cut, so now it is totally simply connected domain. It is simply connected domain. Okay. If we have here three holes, 1, 2, 3. So this is multi-connected domain, and according to holes, if we insert here three cuts here, okay, then this has converted into simply connected domain by inserting three cuts. So number of holes will be equal to number of cuts. This expression makes multi-connected domain into simply connected domain. Okay. Next, so we come to main theorem, Cauchy theorem. This Cauchy theorem depends on some simply connected domain. If f is analytic function in simply connected domain D, and gamma is any simple closed rectifiable contour in D, then integration of this function fz along this curve C gamma will be 0. This is Cauchy theorem, and I am not discussing here proof of this theorem, because any book you can see the proof of this theorem, any book. So there is one remark, and very important remark, because some confusion always there. Since the interior of a simple closed contour in a simply connected domain, Cauchy theorem can be stated as, you can see like this. You can read this theorem like this. If gamma is a simple closed contour, simply closed contour, and the function f is analytic at each point on and inside gamma, then this will be 0. So the interior of simply closed contour is a simple connected domain. Okay. अगर ये है, then Cauchy theorem can be rewritten like this. So this is Cauchy theorem, and we can take some question. You can see this is a polynomial of degree 3. This is a polynomial of degree 3, and this is every polynomial is analytic. In the morning session, Dr. Anupata Gupta has discussed things about analytic functions. So this is polynomial, this is analytic function, and we have to find out this contour integration, value of this contour integration, where C is unit circle, and C is squared with what, say 0, 0, 1, 0, 1, 1, and 0, 1. So you can see, and the solution of this part, so this part A. So this is a unit circle, and you can see here, this is a simple and closed, as well as the interior part of this simple closed rectifiable curve is simply connected domain, because we can shrink this circle to a single point where that is origin, that can be origin. So this function is analytic at each point. You can see here, this function fz is analytic at each point of this domain. So by using this Cauchy theorem statement, contour integration of this one will be 0 because fz, this polynomial is analytic function. This polynomial is analytic at each point of this this circle, unit circle. In similar way, again, this is a square, and this same function, polynomial function, is analytic at each point of this square. Therefore, use Cauchy integral theorem, we can say the value of this contour integration is 0. We come to question number 2, 1yz. 1yz. If fz here, 1yz. Now you can see easily this fz is not analytic at 1y, not analytic at 0. Z is equal to at z is equal to 0. This function is not analytic because this function is not defined, not continuous, not differentiable, not analytic. So f z is equal to 1 upon z is not analytic at z is equal to 0, but 0 lies in this simply connected domain. So Cauchy integral theorem is not applicable here. So we cannot apply here Cauchy integral theorem. Easy example, but we can also determine this the value of this contour integration by using Cauchy integral formula. We will discuss later. And also in this way, z is equal to if we put z is equal to a to the power iota theta, because this is a unit circle, so dz is equal to a to the power iota d theta, and theta is going from 0 to infinity, 0 to 2 pi, 0 to 2 pi. And if we put the value of z and dz here, and in the polar form, then we get the value of 2 pi iota, which is non-zero. So if function fz is not analytic, then value of this contour integration may be non-zero, may be 0, depends on the question. So we can see third example, integration of this function fz is equal to 1 by z, and again what is c? C is again a unit circle. Sorry. This is unit circle, not exactly I am able to draw here by using mouse. So fz is not analytic at 0, and 0 belongs to this unit circle. So Cauchy theorem does not hold. So Cauchy theorem does not hold. So finally, we can see here, if we put z is equal to e to the power iota theta, same whatever we have done in a line integral like this, if we do like this, so we get this expression, and this is I am not saying that this cannot solve, but this is more complicated. So we avoid. So we can determine the value of such contour integrations by using Cauchy residue theorem. So tomorrow you will learn Cauchy residue theorem. So I am not discussing here Cauchy residue theorem. Next, we come to deformation theorem. Let gamma 1 and gamma 2 be positively oriented, simple. Positive oriented means anti-clockwise, simple, closed contours with gamma 2 integral to gamma 1. If any function fz is analytic on the closed region containing these two, and the point between them, then integration of fz along this gamma 1 will be equal to integration of f2 along with this curve gamma 2. You can see here, this is gamma 1 and this is another curve gamma 2 which lie inside this gamma 1, and both are anti-clockwise, and this function fz is analytic between these curve gamma 1 and gamma 2 and on this curve. Then what we see, we have this result deformation. This is known as deformation theorem. So there are some questions related to contour integration we can solve using this deformation theorem. So I'm not giving so much things here related to this one, but I'm coming at Cauchy integral formula. Let gamma be a simple closed same thing, positively oriented contour, same condition gamma satisfies here. If fz is analytic function in some simply connected domain S that contains this curve gamma, and z0 is any point inside this gamma, you can see here S is simply connected domain. This is simply connected domain, and this simply connected domain contains this simple closed rectifiable curve gamma, and z0 is a point which belongs to this interior part of this simple closed curve of this gamma, and then the value of this contour integration fz upon z minus z0 dz is equal to 2 pi iota function of value of the function fz at z is equal to z0. This is Cauchy integral formula. You can see here the value of this contour integration e to the power z upon z minus 4 fz is equal to e to the power z z minus 4. This function is not analytic at z is equal to 4. This function is not analytic at z is equal to 4, and we have to see this z is equal to 4 lies or does not lie in this domain. C is a circle which is given by this expression z minus 6 is equal to 3. So 6 is the center of this circle, and radius is 3. So this point is 9, and this is 3 comma 0. So we are able to see this 4 lie inside this domain. So so this function is not analytic. So Cauchy theorem we cannot apply here. So finally, what we do, we should look for Cauchy integral formula. According to Cauchy integral formula, we take fz is equal to this fz is equal to this exponential function e to the power z. This is analytic throughout this complex plane. So throughout this complex plane means each and every point of this domain, this function fz is equal to e to the power z is analytic, and z0 belongs to 4. So according to this expression, what we get by Cauchy integral formula e to the power z is equal to 4 1 upon 2 pi iota. You can see here. So this is the value. Simple example. I am try to give some clarification, some how to apply this Cauchy integral formula in the question. So this is one question, and this is another question. Function is same here. Fz is equal to 1 upon z minus 2. Fz is equal to 1 upon z minus 2. This function is same, but domain or circle or C, that is a curve, that is different. So circle first is center 2, radius 4, center 1, radius 5. Another is in part C. There is one rectangle with vertices 3 plus minus 2 iota and minus 2 plus minus 2 iota. Am I audible? Hello? Hello? Hello.
Yes, sir, you are audible.
Okay, thank you, thank you. So third C is rectangle with what says 3 plus 2 iota and -2 plus -2 iota, and fourth one is triangle. So you can see first one. So fz is equal to 1 upon z minus 2 is not analytic because this is rational function and this is not defined at z is equal to 2. So it is not defined at z is equal to 2, so it is not analytic. And 2 lie in this domain. Here you can see 2 lies in this domain. So Cauchy integral theorem is not applicable, but Cauchy integral formula we can apply here. Here we can take z naught is equal to 2 and fz is equal to this constant function 1, which is analytic for C. So by using Cauchy integral formula, the value of this one is equal to 2 pi I. If we take another part B, so again the same thing, center 1, radius 5. So this is 4, this is 6. It will 6 here. So value of this one, contour integration remains same. If we change this circle from this one to this one. Next we come to a rectangle. Rectangle means same thing. We are able to see here fz is equal to 1, z naught is equal to, simple example I am explaining here. So this is again same value, and you can see here z naught is equal to 2. In the if we take this triangle with what say 0 0 1 comma 0 0 comma 1, z naught is equal to 2, which does not belong to this triangle with vertices, neither in interior part or nor on the boundary of this triangle. Therefore, this is analytic function. So Cauchy theorem, we can write the value of this one 0. So this is another example. I'm not explaining this one. And some important fact regarding this analytic function. So one is Morera theorem. This theorem is converse of Cauchy integral theorem. But this theorem says this, the statement of this theorem is this: if a function fz is continuous in this domain D, such that integration of contour integration of this function fz with respect to z is equal to along this contour C is equal to 0, where C is simple closed contour C in simply connected domain D, then fz is analytic in domain D. So this is Morera theorem and this is Rivera theorem. If fz is entire and bounded function, then fz must be constant. One best example, one best thing of this theorem, I feel, in trigonometric, in real analysis, we say sin x is bounded function. Sin x is bounded function, bounded by 1. Mod of sin x is 1. But in complex analysis, if we replace x y z, so what we get, function of z will be sin of z. So sin of z should be bounded or not? Many professors ask sometimes in interview, sin z is bounded or not? But sin z is not bounded. It is unbounded, because by using this theorem, sin z is an entire function. Entire means analytic throughout the complex plane. Sin z is analytic throughout the complex plane. So this is entire function. Okay, and if it is bounded, then it must be constant. But this is not constant, so sin z is bounded, where sin x is unbounded. So this is the fact. This is the one related to this Rivera theorem. So next we come to zeros of analytic function. Zeros of analytic function, any point z naught. This is basic definition. In context of fundamental theorem of algebra, but a point z naught is called a zero for the complex valued function fz if fz is analytic at this point and fz not first derivative of f at z naught up to m minus 1th derivative of f at z naught is 0, but mth derivative of f at z is equal to z naught is non-zero. A zero of order 1 is called simple zero, and this definition also can be written like this: if f is analytic function defined like this, and any point z naught belongs to this set G satisfies this condition, then z naught is a zero of the function f of multiplicity m of order m, which is greater than equal to 1. If there is an analytic function, another analytic function G, such that fz is equal to z minus z naught to the power m gz, and G satisfies this condition. G of z naught should not be 0. So you can see 3 examples. Zeros of sin z. Sin z, we can say sin z is 0 at n pi. N belongs to set of integers. So these are the 0. And you can see here another example, z square sin z. So z square, we can expand this sin z is equal to z minus z cube by 3 plus up to so on. So we can take common here. So z cube, 1 minus z square by factorial 3 plus z to the power 4 factorial 5 and so on. So this expression can be written like this: z cube into gz. Here gz is equal to this function, this series expansion of the function. It is noticed that the function f has a 0 of order 3 at z is equal to 0, because g0 is equal to 1, which is non-zero. This is second example, and this is third example. Simple, just I make this sin z cube. Nothing is tough or great here. Just one can understand the concept of zero by this example. So we can also justify, because in the morning session Taylor series has discussed by Professor Akshi Milker. So I thought I should give this Taylor series approach to define the zero of analytic function. So rather than fundamental theorem of algebra. So since fz is analytic at z is equal to 0, you can see the Taylor series expansion. If fz is analytic at z is equal to 0, then Taylor series expansion of fz is written like this: fz is equal to summation j is equal to 0 to infinity aj z minus z naught power g on some disk with center 0, radius r. Here aj is equal to fj z naught. Fj means jth derivative of function f at z is equal to z naught. If fz has a 0 of order n, then that first definition, this will be 0 and this will not be 0. Thus, what see, we get a naught, a1, a2 up to am minus 1, up to am minus 1 from this one will be 0 and am will not be 0. Hence, this expression can be written like this. If this fz has a 0 of order m, you can see here, this is Taylor series approach: am z minus z naught to the power n plus am plus 1 z minus z naught to the power n plus 1 and so on. If we take common from here, this expression can be like this, and this can be put here gz, and if gz is equal to this one and that satisfy this condition, and this is also analytic in this one. So finally what we say z is equal to z naught is a 0 of order M for this function fz. This is Taylor series series expansion approach, and conversely, let fz is equal to this function what we have got in this way, and since gz is analytic as z is equal to z0, it has following this Taylor series expansion summation. J is going from 0 to infinity, bj j minus z0 to j, and since this is non-zero at z is equal to z0, so b0 will be non-zero. Thus, we have this expression for fz, which shows that the function f has a 0 of order m. Thus, we get this if and only definition for zeros of f. Let fz be analytic function at z0, then f has a 0 of order m at z0 if and only if fz can be written like this: z minus z0 to the power n gz, where g is an analytic function at z0 and satisfying this condition. This is a Taylor series approach. This is an alternating way of defining a zero order. There are some observations I have noted here from some book. So when a function fz has a 0 or at z0, but has no other 0 in some neighborhood of z0, then it is known as isolated 0. Isolated 0. In some this is related to isolated or non-isolated 0. In other words, z is equal to z0 is an isolated 0 if fz, if there is a small real number delta, positive small real number delta, such that there is no other 0 of fz in the domain, this one. If there does exist such delta, then the point z0 is called non-isolated 0. Okay, isolated, non-isolated, singularity will come. No, it has discussed. Singularity also has discussed. So non-isolated and isolated things you have known already. So finally, we come to another observation. If there are two functions fz and gz, analytic function which are analytic as z0, if fz has a 0 of order m and g has a 0 of order n, then f dot g multiplication has a 0 of order m plus n. You can verify this observation by using these examples. These examples. This one. You can take this is fz, this is gz, and you can see the things related to this observation. Next, another observation. Any function f is analytic on a domain S, and fz is equal to 0 at each point z of a subdomain of S, or an arc contained in S, then fz will be 0. So by using this observation, we can show sin square z plus cos square z is equal to 1. This because this entire function has 0 values along the real axis. Along the real axis 0 value, thus sin square z plus cos square z minus 1 is equal to 0 throughout the whole complex plane. Therefore, we can establish this identity using this observation. This is the one thing. And if function fz, another observation related to 0, if a function fz is analytic on bounded domain S and continuous and non-vanishing on the boundary of S, then fz can have at most finitely many 0 inside S. Thus, final conclusion, thus an analytic function can have an infinite number of zeros only in open or unbounded domain. So this is the some facts about zero of analytic function, and for preparation of this content, in preparation of this content, I have referred these books. well-known books. John V. Conway for complex analysis, R.P. Agrawal, and Visual Complex Analysis by Needham, Introduction to Complex Analysis by E. Taylor. I have gone through this. I have used these 4 books in the preparation of this talk. Thank you. If any question, the most welcome. Hello. Hello. Am I audible? Hello.
Sir, just 1 minute.
Hello.
Sir, there's a question in the chat box.
No,
Sir,
no.
Anjita.
Answer is no. Answer is no. I have explained this one also. If function is analytic, then value of complex integration does not depend on the path, only depend on endpoints. You can see here. I have taken one example related to this one. This one. I have taken this example, so answer is no. Another question? Hello.
No more questions, sir.
Okay.
Only this much questions, Paki?
Ma'am, actually, a student asked a question in the chat box.
I have answered. If any student has some more questions, then I try to give answer.
Sir, I think no more questions are there.
Okay.
Thank you, sir. Thank you, sir, for your valuable words. So now I would like to request all the participants and to switch on their video. And sir, please turn on your video so that we can take a group photo. Thank you, sir. Paki, you can take the screenshot.
Yes, ma'am, done.
Okay. Thank you, sir. Thank you for joining the workshop. Thank you,
Okay.
sir.
Welcome. My best wishes to you all. Okay. So should I leave?
Yes, sir. Yes, sir. Yes, sir. We can close
you.
the event.